Hello everyone, this is the first of a three-part lesson on vectors. The three lessons will fully and completely cover the topic of vectors for students at the CXC CSEC level, and it will prepare them to master any question on vectors that they may encounter during the exams. In Lesson 1, we introduce the topic and provide a simple and intuitive problem-solving method that we would like to recommend. Our students sometimes refer to this as walking the vectors. In Lesson 2, we solve problems. Detailed solution to several examination level questions. In Lesson 3, we continue solving problems, but with a focus on applying vector techniques to geometrical shapes. Okay, so let's get right over to our first lesson. Okay, so let us get started with lesson number 1. And before we jump into this lesson, I want you to just pause for a moment and think about what a vector is. When I think about a vector at this level, I think simply about a vector as a line connecting 2 points. Any 2 points. Let's call this point A. Let's call this point B. And if I have a line connecting those 2 points, then that line is my vector. So I will attach an arrow to it because the vector is defined with a direction. So I would like you to consider the vector as simply a line connecting 2 points. And the line has a length because I could have a different line with a different length. And it has a direction, and the direction is denoted by an arrow. So if I were to define or to use a symbol to represent this vector, I could think about one way of doing it as 2 uppercase letters, the letters here representing the points, and an overhead arrow indicating the direction of that vector. So the vector is a line connecting 2 points and it has a direction. It does not get any simpler than that. The vector is a line connecting 2 points and it has a direction. And that is important because if I use another vector here, CD, I could go in this direction as well. And then I would write my vector as CD, indicating that the vector is going between the points C and D, and the arrow is indicating its direction. So one form of representation is 2 uppercase letters with an overhead arrow. There is another form of representation that I would like to show you here, and that is the vector can be viewed as having 2 components. The first component is what we call the x component, and that is just the number of units in the x direction. So for example, if I start here at 0, I would count 1, 2, 3, 4, 5 units in the x direction, and then I could start here at 0 and count 1, 2 units in the y direction. So I have 2 components that I could use to represent the vector, an x component of 5 and a y component of 2. So as a column vector, I could write 5, 2. So I could represent the vector in the form of a column matrix or a column vector, and we could say it's A, B. I'm using lowercase letters here to represent the size of the vector as opposed to the 2 points, which are A and B and denoted in capital or uppercase letters. Finally, I could also use a lowercase letter to represent the vector, and I could use any letter. So in essence, a lowercase letter, let's use 1M here, can also be used as one form of representing the vector. So where are we? We have an idea what a vector is. We have an idea how to think about it. It's just a line connecting 2 points, and it has an arrow to indicate the direction. And we have identified at least 3 ways of representing that vector. Okay, so I would like to represent a few vectors on a graph. Why do I want to do this? Because I want you to become comfortable with the simplicity of seeing vectors simply as lines moving between 2 points. If you have that in your mind, half of the journey is already completed. So let us look at the first example here. I have example number 3, and I'm just going to be drawing some lines on a graph to show you what a vector would look like. So in the first case, I have OA. So O here is referring to the origin. So let me put an O here and the origin at coordinates 0, 0. So I have the first vector, and if you remember our representation of the vector, I have the first vector OA. Let's write it down here, and we say it is 3, 4. So recall that for our coordinate geometry, if we go in the positive x direction, we are going to the right. That's what we call positive x. If we are going up, we call it positive y. If we are going down, we call that negative y. And if we are going to the left, we call that negative x. That is our sign convention for two-dimensional coordinate geometry. That is how we're going to treat it. So OA then means I'm going 3 units in the x direction and 4 units in the y direction. And it is always x, then y, never the reverse. It's an ordered pair. So this then means OA is going 3 units to the right and 4 units up. So 1, 2, 3 to the right, 1, 2, 3, 4 up. So point A is here. So now that we have the point A, we can draw the vector OA. What is the vector again? It's the line connecting the points O and A going in the direction of A. So we simply draw the line between O and A. So let's describe it as going from O to A in the direction of A. So that's our vector, going from O to A in the direction of A. And I can put an arrow on the line because vectors are not completely described without putting the arrow to indicate the direction. So now that we have the vector OA, let us proceed to draw the next vector given, which is AB. And AB, the vector going from A to B, is described as having the x component is -2, the y component is 4. Now notice what we're doing here. We're now going from A to B. From A to B, which means we're at A going towards B. And we're going, based on our sign convention, we're going 2 to the left and 4 upwards. So 2 to the left is 1, 2, and 4 units up is 1, 2, 3, 4. So this is our point B. Let's quickly draw the vector AB. And there we have the line representing the vector AB. It is incomplete unless we put an arrow to describe its direction. So let us do that now. Here's arrow, and let's identify as AB. So item 1 is asking us to identify the coordinates of B. Well, that can be extracted directly from the graph. So we're now asked to draw the vector BC. So we're at B and we're going towards C, and we're given information as to how to get to C. So we have this, right? BC is going to be moving -4 and -3. This tells us it is -4 to the left, -3 down. So we're going to go to the left again 4 units. So it's 1, 2, 3, 4, 3 down, 1, 2, 3. So point C is here. So once we have identified the point C, we can now connect the line between B and C, which is what we call the vector. And what are we going to do immediately? We are going to attach an arrow to indicate the direction of the vector going from B to C. I think we're making progress in terms of seeing how the vectors look on a graph. So let us continue to item number 3, where it says find the vector going from C to O, where O is the origin. Here's the O. So draw the vector from C to the origin, which is a vector CO. Let's just label. So we have 4 properly labeled vectors. So now let's look at part 4 of the question. It says, what is the difference between the vector CO and OC? Okay, Well, let us find out what CO is. So let us write CO is equal to the vector from C to O. So let's take our X displacement first and our Y displacement, because that is how the column vector is going to be specified. So we're going to go to the right, 1, 2, 3, and we're going to go down, 1, 2, 3, 4, 5. Now, since we're going down, we know it's going to be negative 5. Positive 3 because we're going to the right, but negative 5 because we're going down. Now let's look at the vector O to C. And if you notice immediately, the vector O to C simply means that the vector has the same size, but it is going in the opposite direction. So let us go in the opposite direction, starting at O, going towards C. So first, X would be 1, 2, 3. So I'll have negative 3. And Y would be positive because I'm going upwards. So it's 1, 2, 3, 4, 5. So O to C, the vector, is equal to negative 3, positive 5. Now, if you can see what I'm seeing immediately, then I am seeing immediately that CO, the vector CO, is really negative 1 times the vector OC. So this is an important observation. It is telling us very early at the start of lesson 1 that the vector CO and OC are related because they represent a vector with the same size or the same length, but they are going in the opposite direction. Very important to learn this quite this early in the game. So let's continue. Okay, so now we need to know what we mean by multiplying a vector by a scalar. To multiply a vector by a scalar is simply saying that if you have a vector AB and it is equal to 2, 3, then it is possible to multiply AB by a scalar. What is a scalar? A scalar is a real number. We sometimes also refer to it as a constant. So a scalar is simply a real number. So 2, 1.5, negative 3, negative 1.5, those are all scalars. They are simply real numbers. So in fact, if I have AB is equal to 2, 3, then 2 times AB is equal to 2 times 2, 3, which is equal to 4, 6. And by extension, I should be able to take a factor of a vector. If I can multiply by a scalar, I should be able to extract a scalar or any real number from the vector. So for example, the vector CD, if the vector CD is equal to 9, 6, I should be able to say that CD is equal to, and I take 3 as a factor, and this would be 3, 2. So I should be able to say this as well, and in fact I can. So multiplying a vector by a scalar is possible when dealing with vectors. So what are the different types of vectors? Well, first we have something that is called a position vector. The position vector is a special vector used to identify the position of a point. So for example, if I have a point P here, then the position vector simply helps me to identify where this point is located, and it uses a vector starting at the origin to do that. So it always starts at the origin, so I'll write O for origin. So since it is a vector, we have to define it as such or describe it as such. So we have to attach an arrow saying it's going from O to P, and of course OP is the representation of the vector. Okay, so this is the position vector. So let's just write, this is our position vector. So we can say the position vector always starts at the origin. So that's as much as we want to say about the position vector at this time. It's a vector that is used to identify the position of a point, and it starts at the origin. So item number 2, the negative vector, what is that? The negative vector we encountered a little earlier, because a negative vector simply describes a vector with the same size going in the opposite direction. So for example, given here that OP is equal to 1, 2, 3, and 1, 2, 3, 4, 5. So it is 3, 5. Then PO, the negative vector, will be going in the opposite direction. It should be going in a direction like this, starting from P. So to define the negative vector, or to define the vector PO, the x component would be 1, 2, 3 to the left. That's negative 3. And it should be 1, 2, 3, 4, 5 down. That's negative 5. Which can be written as negative 3, 5. Which is the proof that PO, or rather OP, is equal to negative PO. Expect us to use that principle very regularly as we go forward. Now, equal vectors. Now, what do we mean by equal vectors? Okay, so here we have a case of 5 vectors, and the topic is what is an equal vector? It is defined explicitly as vectors with the same size and direction. So, for example, the vector j to k we know to be the same as a to b, and that is the same as c to d, and that is also the same as h to I. So all these vectors 1, 2, 3, 4 are all equal. So let's just identify the equal vectors. So this vector is equal to this one, and to this one. However, the vector FE is going in the opposite direction, so this one is not equal. So we could write FE is not equal to AB. So an equal vector simply means the same size, same direction. Let's continue. Parallel vectors. So we note that all these vectors are parallel. They do not have to be going in the same direction to be parallel. Let's write a definition for the parallel vector. 2 vectors are parallel if one vector is a scalar multiple of this other vector. What is this saying? So if this is vector AB and this is a vector CD, then AB is parallel to CD if CD is equal to a scalar multiple or a constant multiplied by AB. That is a single requirement for vectors to be parallel. So this is a very important observation, and we need to recognize it early because we're going to be using it regularly to test whether vectors are parallel. So if I have vector HK is equal to 9, 6, and I have vector IJ is equal to 3, 2, then are these vectors parallel? So I would test to see if HK is a multiple of IJ, vector IJ. So I would say, okay, let's examine HK. So HK is equal to 9, 6. I could take a factor of 3, and I would get 3 into 3, 2. But 3, 2 is equal to IJ. IJ is equal to 3, 2. So I could write as 3 times IJ. So in conclusion, since HK is a multiple of IJ, then they are parallel. That is as simple as a proof can get, and it does not need to be any more complicated than that. So if we need to test if 2 vectors are parallel, this is how you go about doing it. So let us move on to the final part of lesson 1, and that is collinear points and what are they and how to prove that points are collinear. So first, let's define what collinear points are. So points are collinear if they lie on a straight line. So let's just imagine what that looks like. This is A, B, and C. 3 points. We are asserting that if these 3 points lie on a straight line, then there is a vector method that is available to prove that. So let's just take a look. So there are 2 conditions that need to be satisfied. So the first condition is that we need to show that lines connecting the points are parallel. That's condition 1. And condition 2, the lines must share a common point. That's condition 2. So if we can satisfy those 2 conditions, we can assert that the points are collinear. So here are lines connecting these points. So here's the first line. So this line connecting these 2 points, I can give a name to that. I could call this a vector. A vector is a line connecting 2 points. So I could call this a vector. So I could call this vector AB. I could do the same thing for the line connecting B and C. That is also a vector. So I could call this as vector from B to C. But there's also a third vector. And if you look closely, you will see it. But I'm going to show it to you. It is a vector going all the way from A to C. Because A to C, the line connecting A to C is also a vector. So if I just imagine that that vector is that line here, I could just write all the way from A to C is also a vector. So we have 3 vectors. We have AB, we have BC, and we have AC. Now if AB, the line, is parallel to BC, the other line, then we can say that we have satisfied condition 1. But AB can also be parallel to AC and AC to BC. So let's write down the 3 conditions that we may have, or the 3 pairs that we can consider. So I could consider AB being parallel to BC. If this is the case, then the lines are parallel. Or I could test that AC is parallel to AB. That's another test I could do. I only need to do 1, but I have options, because there's also AC and the test of whether or not that is parallel to BC. So I merely need to choose 1 pair of vectors, and if they are parallel, I have satisfied condition number 1. What is the proof that 2 vectors are parallel? It is simply that 1 vector, in this case AB, is a multiple, a scalar multiple of BC. Recall we did that test earlier. So once I can prove that any of these pairs of vectors are multiples of each other, I would have satisfied condition number 1. It's as simple as that. When we start looking at problems, for the second condition, what does it mean that the lines must share a common point? Well, AB and BC share this point. A to B, this point is common to A. BC, this point is common to BC. So B would be a common point if I was considering this pair. If I was considering AC and AB, then I would expect A to be common between the 2 of them. And if I'm considering AC and BC, then C would be common. So let me just show you that. So if I'm considering AB and BC, B is common. If I'm considering AC and AB, A would be common. And if I am considering AC and BC, C would be the common point between those 2 lines. So in all cases, I can identify a common point, and that would satisfy condition number 2. Okay, so here's a quick review and summary of what we did in lesson 1. Number 1, treat the vector simply as a line connecting 2 points. That is an excellent way to conceptualize the vector. For example, a line connecting the points A and B with an arrow. It doesn't get any simpler than that. 2, the vector can be represented in different ways. Recall that we can use 2 uppercase letters with an overhead arrow. We can use a column vector format, or we can simply use a lowercase letter to represent the vector. 3. The position vector is a particular vector that starts at the origin. So it begins with an O for origin, looking something like this. 4. To reverse the direction of a vector, simply multiply the vector by -1. Number 5. Two vectors are said to be parallel if one vector is a constant multiple of the other vector. And finally, points are collinear if the vectors connecting the points are parallel, and B, if one point is shared by the vectors. So very simply, 3 points are collinear, 1 point is common, and these two vectors are parallel. Vector A and vector B are parallel. So that is as much as we're going to do in lesson 1. Let's head over to lesson number 2 where we can solve some problems. See you there.